Yes, sir. Sir, myself is a assistant professor in agriculture university, CSS HUG Haryana Agriculture University, and I'm working on same
Mhm.
type of these type of images. So
हम्म,
we
आपको बेल सर
how
पता है
much?
ना? बेल सर, बेल, प्लांट पैथोलॉजिस्ट.
Yes, sir. I just started this work. I'm going to like to start this work. So any suggestions like that you want to give me that how close I take the images or what cameras or what
Sir,
hardwares
first,
like that?
yeah. Sir, first,
Mhm.
you require the tensor flows, sir, and
Yes, sir.
any the what they call sensors assembled persons. If you are around areas, if it is available, so better to consult with him. Then we need to fix up 4 5 sensors, or we need to embed 4 5 sensors together. Then basis on that we can write a program and it will work it out well, sir. But
Okay,
we
sir.
require the sensors. Then we need to embed it.
Oh, okay, sir.
The programming is a
Thank you.
little bit easy, but
Yes, sir.
embedding is a little bit task.
Okay, okay, okay. Thank you, sir.
Thank you, sir. Krupani sir, kindly conclude the session, sir.
Yeah. So good afternoon to you all. Immensely happy to have Dr. Shyam Perugu with us. He is very well known to our Department of Biotechnology at VIGNAN'S University. He is a regular visitor. He is our Board of Studies member. Young person we have got in our university, the Board of Studies member means it is only Shyam Perugu, sir. Everyone in our department is quite familiar with Dr. Shyam Perugu. And we are immensely happy for accepting our invitation, Abraham's invitation, to be the webinar speaker today. And Sir has given a very excellent personal experience in agriculture, coupled with his academic experience in R statistics and bioinformatics, everything very nicely presented, particularly with regard to the infection, incubation, inoculation of plant pathogens, optimization, optimal temperature, relative humidity, soil fertility, soil moisture, pH. This all constitute the data set, node repository, and all these ML applications. So SAR also has given several other image analysis relating to the diagnosis of plant diseases. He was mentioning plant to plant, this type of the data set varies. So that's another important thing. Next, also, SAR was mentioning about sensors. It's important, about all which we have to learn a lot through him. And both the agricultural aspect of it and the image analysis aspect of it and tensor flow and all those things very neatly elucidated for every one of us, suiting very well to our biological background. Thank you all. Thank you, Dr. Shyam, for having given wonderful talk today. Thank you, Pranab.
Thank you, sir. Thank you for the giving opportunity, and it is my pleasure to have to interact with the participants and you, sir. Thank you. Thank you once again, sir.
Thank you.
Bye.
Thank you, Perigusham, sir.
Thank you, sir. Thank you.
Thanks. And next, coming to our next invited speaker, Ms. Estela Cabbages. She obtained her bachelor's degree in the field of biotechnology from Central University of Catalunya, Spain, and obtained her MS degree from University Carlos III of Madrid, Spain, in the field of management and development of biomedical technologies. She worked as a research technician at Hayem University of Applied Sciences, Finland, and also at Central University of Catalunya, Spain. Later, she worked as solutions architect at IZON, Barcelona. During this period, she worked on documenting, testing, and improving solutions to track real-time data and performance of pharmaceutical plants. And also, she worked as a data science analyst at Accenture. As a part of the Accenture Applied Intelligence team, she helped clients to deliver more effective, efficient, and affordable healthcare. Currently, she is working as a deep learning research technician at University of Carlos III of Madrid, Spain. Estela has volunteered her time to many events representing the leukemia AI R&D projects as an Intel software innovator. She speaks Catalan, English, and Spanish languages. Estela has earned Intel DevSpace AI Spotlight Award 2019 and Intel Software Innovator Award. With this note, I'm happy to invite Estela to present her work.
Hi, good morning all. Thank you for this kind introduction. It's a pleasure for me to be here. So let me share my screen. So today I will be talking about some applications of biomedical technologies, all based in artificial intelligence. So before starting any AI project, there are some things that we have to have in consideration, mostly if we are talking about the health sector. For example, as who has permission to treat the data we are going to use, if we are working with some kind of organization or with a health organization, is there any session contract between the parts to lead the researchers to treat this data? Some other considerations are, for example, which legal regulation does apply to your country or region? Because, for example, here in Spain, we have a real clear regulation about it and which is considered sensible data and which kind of data transfer we must apply if we are doing, for example, international data transfers. And lastly, but not least, is if we have a workflow pipeline. So how are we going to provide this project and how are we going to work through this project? So to start with, as you might be able to see in the different projects the speakers have been providing during this e-workshop, we need to find the data value. So, for example, what data do I have? So do I have images? Do I have electronic health records? Or do I have omic data? Of course, we need to be sure about how this data is acquired. So, for example, which methodological applications are we extracting the data from? For example, are we using microarrays if we are talking about omic data? Or is it data that it's manually written by health staff? Also, where does this data come from? So does it come from an open source database? Does it come from a really closed source? Also, as we've been saying, so what will I use this data for? And super important to know and define which real question do I want to answer. Here are some examples of data value we can extract if we are talking in the first column about electronic health records. We can extract information about hematology. So for example, blood samples, which kind of biomarkers are we trying to observe and to get conclusions from? Are we doing a social demographic study? For example, is a disease affecting more one region than the other? Also, we can study the time a patient is being admitted into the hospital and being discharged. Is it a long time that it passes through, or are we being optimal on treating this patient? We can also talk about images. So are we studying computed tomography images or magnetic resonance images? Or of course, are we talking about surgical videos to improve surgical skills? Also, another data source that you have been able to see during this workshop is omics data. So are we analyzing genetical data? Are we analyzing proteomic data? Or indeed, we can also study metabolomic data and other kind of omics. So that's why we really need to be sure about the source. So how and which methodology is applied to acquire all this data. When we take a step forward into our project, we can use different methods, applying into AI, of course. So for example, are we using a supervised learning to develop predictive model based on both input and output data, as for example, classification or regression models? Are we using an unsupervised learning So are we grouping and integrating data based only on input data? Or another example might be the reinforcement learning algorithms, which is the area of machine learning concerned with how intelligent agents ought to take actions in an environment in order to maximize the notion of cumulative reward. In that case, we can use Markov decision processes based on the most probable path based on weights, or for example, the Monte Carlo algorithm, which can be used to mimic policy iteration, usually taking into 2 steps. Another thing during the methodology that we need to take into account is if we need extra hardware to produce our project. For example, if we are talking about some electronical health record data, we might not need a high processing equipment, so we can just work it with RStudio and our CPU. But if we are talking about a high load of images that are really heavy and our model requires a lot of processing, we might need a GPU in that case. Of course, there are many online platforms that provide this, so you don't really need to have a GPU at your place or at your house or your working place. And there are also many operating systems that we can use. Also, another requirement are the drivers required by this hardware, to say it like that. So for example, some networks might require some versions and we need to choose which driver version we want to install. For that, there are many processes and many decision processes to make that call. And finally, another thing that we need to take into account is the storage capacity that we need. If we are working on a cloud, then we might not have that problem. But if we are working on a hardware and physical equipment, we might need some gigabytes or terabytes to, one, store our data and to store the model that is going to be processing all this data. Also about the disk space, do we need a really quick SSD disk storage or not? So with that, I just want to provide you with a critical thinking of how to start a project. So let's go with some examples I have gathered for you that take into account these data sources I have just mentioned. And I think it's really interesting for you to take a close look to these articles. In all of them, you have the reference if you want to go later on to this article and see how they are implementing artificial intelligence. So in this first example, we will be seeing how we can classify electronic health record information. So for example, if we are talking about respiratory disease as interpretation of pulmonary disease or ventricular dysfunction, we can use a natural language processor, which enables interaction between computers and humans, following rule-based algorithms or machine learning approaches. Natural language processor algorithms are complex and perform multiple tasks as extraction, information processing, and processing it in a patient level with ensured criteria data. For example, in this first part here, where we have the clinical notes, which are usually unstructured because we have different agents interfering in these electronic health records. So we do a text processing here to reorder and to structure our data. To keep up and to gather with the criteria, we then provide some concepts that are certain that for this disease, this is going to happen. These facts need to be in the electronic health record of the patient, as for example, the status, the severity, and the control, and if the patients are and caregivers are providing also this information. We just add it all up, and then we do a patient level classification. So for example, if we know and we are sure that for asthma disease, we know that these biological conditions are given, this ensures us to classify this patient as a probable asthma patient. Another example of how to treat electronic health record is explained in this image. In here, we can see the most common architectures for analyzing electronic health records, relying on different nodes and connection structures. If you have a closer look to this article, you can see that there is a brief introduction on what is machine learning and deep learning algorithms, followed by a functional description of its network, providing the most likely equations to use. So for example, as we saw before, if we are talking about image extraction, we might use, for example, natural language processing or text mining. If we want to analyze temporal events and extract them, we might use recurrent neural networks. These recurrent networks are really useful when we have sequentially ordered data. If we want to do a relationship extraction, we can use classifiers as convolutional neural networks. Or if we want to do an abbreviation expansion, we can also use, again, natural language processing algorithms to map the data towards structured concepts. For example, if we have a technician that writes notes in an electronic health record, used and based in abbreviations, we can just make a forward step and map it for what we know that it's sure. And finally, but not least, about this set of electronic health record examples, we can connect it to pathologies. So for example, using convolutional neural networks to discriminate the leukocyte levels in an hematological result, or to classify the pathologies from a microscope result, as for example, if this patient is likely to have acute myeloid leukemia or not. What we also can relate the electronic health records to is to PET or CT data. So scans and image acquired from the patient's conditions. So for that, we might need to segment some of the organs in the image and then to see which conditions were explained in the previous electronic health record of the patient. This altogether enables a better diagnosis and prognosis by personalizing clinicians' treatment decisions. For example, if we are seeing in a CT that this patient is more likely to have a lung disease, we can go back to his record and check which lifestyle he has had or she has had. In this table I'm presenting here, you can see a summary of which are the most representative AR publications regarding these topics and gathering all this information together. As we have said, images are also a really important data source as acquired from radiology. So in radiology, what we usually use is an image fusion to understand the raw data, the raw images. In this example, we can see an ex vivo human heart CT acquired from 4 different commercial houses. So when we are seeing these first 2 fusion image processors, we are talking about filtered back projection. In that case, images are reconstructed from projection data, applying a high-pass filter followed by back propagation. This here is a kind of fusion based on hybrid iterative reconstruction, where one of the main goals is to reduce artifacts. Then we applied a backward projection and an iterative filtering to reduce the noise. At the end of the image, space data, at the end, sorry, we have an image which is based on space data, and a forward projection is applied to calculate artificial projection data. This artificial projection data is going to be compared with the true data and identify if the true regions are there or not. In this precise example, we can see here in numbers, the noise levels applied as standard deviations in air. So this provides a comparison between different houses, as we have mentioned before. So how is this data acquired? Which technology we are using to acquire those images? And also which kind of processing we are applying in each one. We can also not only use anatomical images, but also molecular or cellular image analysis. In that specific case, it's trying to demonstrate a typical use case, applying variations in buffer filling level, condensation effects, and Menicius-induced imaging artifacts as with some different parameters. So the ground truth for the neural network training is generated by automatic segmentation of the fluorescence images using conventional methods. They are applying here a slightly defocused image in the data set, in the training data set, which might allow the neural network to better account for the small focus variation. The neural network in that case is trained with pairs of ground truth and brightened images. As we were mentioning before, to do a little bit of backup, in that case, they are specifying that they really needed a GPU to process all this data. So it might be due to the amount of data or to the capacity of the network, of the model that they are trying to train. So once the neural network is trained, during the detection phase of the nucleus of the cell, the learned neural network model is applied to brightified images. So for each pixel, it will predict whether it belongs to a nucleus or not. The result is a probability image, which can be visualized in here and shows in different colors the nucleus of the cell. So some limitations of the label-free are the low contrast, the dust and imperfections from machinery to acquire images, and the high level of background noise if compared with only fluorescence images, as we've seen in this previous one here. So another kind of images we can acquire from hospitals are during surgeries. So when we apply artificial intelligence into surgery, computer vision plays a big role. In that case, AI benefits the patient as the surgeon is capable of augmenting each phase of care. For example, in the first step during the preoperative phase, all the data is collected from the patients in the clinical history, as for example, the glucose levels of the patients, the diets that they've been taking the days before the operation, or the activity those patients have had before. This information allows a more accurate operative plan and with valuable post-operative predictions of care. During the intraoperative phase, the surgeon can mix the electronical health record with real-time imaging. So this can assess the surgery when performing the intervention on which is the most accurate step to take next. And in here, as mentioned before, we can sum it up and sum all it up and then see which post-operative care will this patient need. At the end, what we are having here is a clinical decision support structure for surgeons and also for patient recovery. If we are talking about omics, I'm really proud to provide this article with Salvatore Raielli wrote, sorry. And you can find this article in the link provided underneath down here. It's a really good article, since he will walk through all the steps and all the code you need for omic processing. So the data of this article is acquired using microarrays. And as I said, you can easily follow this tutorial showing you how to import the data, which packages will you need, and he explains you how to filter and categorize all these results. So before providing the final and supervised visualization of the principal component analysis that he's implementing in this article, he also explains how to save the data and the results from the filtering and categorization. So with this unsupervised principal component analysis, what we will endly have is a different set of data classified according acute myeloid leukemia, according to healthy patients, acute lymphoblastic leukemia, and other kind of genetic data obtained from this data set. So when we have seen all these, maybe I went a little fast through these reports, but it's because you can just read them carefully. And I just wanted to bring you a clear insight on the high dimension of all this process of building an AI project based on health data. So there are many things to be taken account. So once we have all these results, we need to express them, right? We need to communicate those results. So first of all, one of the things that we need to take into account is who will be reading this report. So are we going to be giving the results to a doctor, to patients, to technicians, or to researchers? Also, we need to consider which kind of language should we use. So if we are talking with doctors, maybe we are using more medical technicisms, or if we are talking with patients, we want to use a patient-friendly language and communication skills. And it's not only about how we are communicating it, but also how are we going to display these results. So if we are doing an analytical report with technicisms, do we want to add a technical workflow? For example, if someone is going to follow our work, we need to present a real and clear structure of how we did all this process, how we acquire the data, how we process the data, which model we used, and why we used that model. Also, we need to really be aware of how we are explaining the results obtained. So to put all this together one more time, I'm going to talk about a really nice initiative that started in 2018, which is a nonprofit association focusing on deploying AI solutions for leukemia. You can find their blog here underneath, and you can check all the work they are doing. This initiative started as a project and became an established association not that long ago. Their mindset is to provide open source solutions for the leukemia disease. Also, they are constantly looking for volunteers to help with this movement, and also for students to learn with them. So here are some of the projects they work on as, for example, medical technologies, which have mentioned some of them. They work with artificial intelligence, which is the main case study of this talk. They also provide solutions for robotic projects, for assisting medical teams and automating the medical industry. And a really new project they are bringing up is based on virtual reality, augmented reality, and mixed reality. So this is a really new environment, and this is a new point of view that researchers are more and more trying to be into. So to make a brief comment about this mixed reality project, the Magic Leap Acute Lymphoblastic Leukemia Detection System that was developed in 2020 uses the Magic Leap 1 headset to display microscopic images of blood samples containing acute lymphoblastic leukemia positive and negative samples in mixed reality. So this project combines mixed reality with artificial intelligence to provide real-time detection systems capable of detecting acute lymphoblastic positive and negative samples. In this slide, you can see in this image how the user sees through the goggles the images, the blood samples in colored stain, the nucleus, and the interesting lymphocytes. So this detection system was based in this data set here, which you need previous permission to use. It is built under TensorFlow, One API, and OpenVINO technologies, and it now achieves approximately 98% accuracy. And it's hosted on a Raspberry Pi 4. As we said, it's really important to know which hardware you need to produce this kind of technologies. So for this last part of my talk, I want to encourage you to participate in some real case practices. And I propose you to provide a critical thinking of the workflow that you might need to develop these projects. So now I'm going to stop this full screen mode so I can see your chats. And even if you want, you can just use your microphone for it. Was I super fast? Are you still there? Are you bored already?
No, it's interesting, ma'am. You can continue.
Okay. So the first case I'm showing here, all of these three cases are real cases that I have seen through my experience. So let's say that a research institute contacts you asking for assessment to implement an AI model to compare large-scale data sets of protein-protein interactions. So I'm asking you, what would you do first, and what would you answer to this research institute?
Please use your mics, participants.
Excuse me?
Yeah, I'm asking the participants to use their mics.
Yes, you can use your you can use your mics and talk about it, or if you want, I can walk you through this case A, so you see a little bit of the critical thinking, but please feel free to talk anytime you want. So if we are talking, sorry?
Madam Estella will enlist the proteins of that yeast, and those proteins which are interacting with the neighbors, and those proteins which are interacting within the body of the yeast cerevisiae, Saccharomyces cerevisiae.
Perfect. That's a really nice approach, actually. You also might need, in order to use those softwares, you might need to know which kind of data they are trying to analyze, right? As we said, so we need to know which methods they used to acquire this data. I'm sorry, I don't see the chat. I think someone is writing. Oh, see, here, I can see it now. Types and nature of amino acids are essential. Bond and angles. Really good approach also. Perfect. So this is a real article that you can read if you want. So they used in this case several types of data acquisition. The first one was human interpretation from different databases, annotation. So in here we might see discrepancies, and it's really subjective to the person who is trying to do this annotation. Then they used 4 types of in silico approaches, which are interconnection of genes based on their paired presence, correlation identification on genes simultaneously active in the same biological projects, linked genes with a common functionality category and prediction of the functional category of genes with unknown function, and gathering attributes from cloned genes and displays in artificial proteins. Then they used also 4 experimental technologies, which was inducible lethality of 2 non-essential genes that when expressed together are fatal for the organism. Also some mass spectrometry and purified complexes. And they also used the yeast to hybrid assay to identify by the production of a functional transcription factor within a pair of proteins. So for the visualization, what do you think would be the most appropriate way of visualizing all this data? There's not a correct answer. It's just a critical thinking exercise. So, for example, we can use this kind of network visualization of interaction between the proteins. In the first one, we can see which kind of method it's apporting more information to our project. And we can also choose one method and see how this method is interacting within it. So how these proteins and which conclusions are we obtaining from the individual method. So for you, how would you automatize all this procedure? So which algorithm would you use? Would you use a supervised or not supervised method? If we are talking that we have an entry with 5,000 data, do you need a faster processor? Supervised, correctly, perfect. Thank you for participating. Awesome. And do you need a faster processor, or you can do with your laptop, for example, or do you need a GPU to process all this data? Maybe with your laptop, you can easily go for it, right? It's not something that might require that much processing capacity. So also, if you have all these results, GPU, oh, nice, GPU, explain me why do you think a GPU is necessary? You can use your microphone if you want. High quality images, perfect, yes, that's true, awesome. See, there are so many approaches, big size. Yes, true. There are many approaches and many decisions that you can take when developing a project. So it's really important to justify and to know why you take those choices. So your project was a success, and now you need to give back these results to the research institution. So which communication language will you use? Will you go for a more technical language? Or will you use a more visual images to see all the interactions that you have found? Large no feature extractions. Yes, that's true. But in this precise example, we were using a text file with this kind of structure here. Maybe I wasn't clear about it. So that's why I was asking if you might need a GPU or CPU. But of course, if you are using images and you want to extract all these features, text mining, okay, that's also a really good answer. For feature extraction, then yes, GPU is super recommended. So now that you have seen a little bit on how to do this kind of thinking, I'm going to just present case B. And you go ahead and you provide me with the answers. So a doctor from a well-known hospital in your city is planning on starting a clinical trial, and the organization you work for is their first option to ask for help. For the development of the clinical trial, they need to standardize the different methods image technicians use for CT acquisition, as they usually put notes in several categories of patients' electronic health records. So, which AI method would you propose to save the doctor's time when looking after those notes? So the doctor gets the CT scans and he needs to go to the electronic health record to see which problems there had been when acquiring these scans. So which method would you propose? For example, we saw the natural language processing, deep learning. Okay, explain me. Deep learning, but which kind of deep learning? Supervised method. Awesome, perfect. Yes, because in this case, you have the labels, you know what you are looking for. But which kind of label in case of a supervised method would you use if you don't know in which category or in which part of the electronic health record the technician has added the information? Classification, perfect, awesome. So would you, for example, use a time classification because you know that at certain time the patient was being in a CT scan, or you can also use, for example, the name of the technician that has written down and actualized the electronic health record. That are super cool ideas. So how would you explain the doctor what you have done? Which kind of communication skills will you use? Will you put just a diagram of how the network works? Or for example, you would do an interface so the doctor can easily add the data he wants to extract and the classification he wants to use? Maybe the second one, right? Interface. Yes, exactly. Perfect. Perfect. So the doctor is really happy with your work, and the first phase of the clinical trial was a complete success. So now this, sorry, before starting into case C, recurrent neural networks. Okay, so explain me why you are choosing recurrent neural networks for this case B. Because we said before that recurrent neural networks are highly desirable for sequentially ordered data. But in here, it seems that we are having a little bit of a mess, right? Because we don't really know where this technician is adding the information. But as I said, there's not a good option. I just want a little bit of objection on whether to use a recurrent neural network. You can tell me later if you want to think about it a bit. So for getting into the last case scenario, in here, as I was mentioning, this doctor asked for you to be the leader and the main researcher in phase 2. So now that you have built an interface to provide this kind of results in phase 1, phase 2 will consist on analyzing all the CT scans acquired in phase 1. But the doctor doesn't know how to segment each organ of interest automatically. So the information we have for this project is that we have 60 patients, that we have 150 CT scans, and we have 6 regions of interest to segment. So we have a brain, we have the left eye, we have a liver, the bladder, the right kidney, and the lungs. So what this is telling us is that there are different anatomical regions to segment. A ROI is a region of interest. So it's the region that you want to analyze in a CT scan. But you can also apply it to not only to CT scans, but also to many other kind of data. So for example, if we are talking about I don't know, about electronical health record, our information of interest can be the social demographic information or the glucose levels or the hematological levels. So for this case, what would you do? So how would you proceed with phase 2 of this clinical trial? Which AI model would you use to segment all these images and to pre-process the CT scans? As we mentioned before, maybe I went too quick through that, but for CT scans from radiology, we commonly use and need fusion image pre-processing. So we might need a really good pre-processing model, right? To understand and to make some masks and to binarize these images in order to obtain our ROIs really clear. Then what can you use? You can use which kind of neural network you can use to segment these organs. You can use a classification model. So when the network is identifying the brain, it classifies it as brain, for example. Yes, no? I guess yes, it's a yes. This silence might be a yes. And as we said before, this doctor doesn't know how to segment these images. So again, how would you teach and communicate your results to the doctor so the doctor uses this network for future patients? Because maybe this phase 2 is also a success and you want to move supervised training data. Someone says from here. Exactly, perfect. Perfect. So to train the doctor to use this this program that you have developed, how would you do it? Again, would you use a technical communication report, or would you just go with an interface? Maybe now it's time to use a more technical communication skills, right? Because the doctor might need to use this network in the future, and some problems can occur, as it happens with most of the projects. So we really need to be sure about what we have done, which kind of supervised training data we used, which kind of labels we used, which kind of masks we used, to make sure that our communicative skills are completely getting into the person we are going to train. So with that, I finished my presentation. I went a bit too fast, I realized, but feel free to ask any questions if you want. And if not, I have here my email, so you can just contact me through email anytime you want. You have these slides, so you can go through the articles we saw. Which AI method or algorithm will be useful for understanding correlation between the SNPs of an organism? Well, that's a really tricky question, as I'm not really into variant identification. BLAST. You could use BLAST, yes, completely. There's also this kind of programs for SNP identification, which is Illumia Variant Studio. It's a free software that you can just put in all the VCF files, the non-annotated variant coding files, and it returns you the possible and the type of classification of these SNPs. As for example, if it's a benign variant or if it's a malignant variant, the probability of, I mean, how it gets into population. For example, if it has a global frequency population of dominant pathology, or if not. So I kind of, if you are really interested in this topic, I recommend you this software because it's really intuitive to use. You're welcome.
A question from our student. Can you see that, Estela?
Yes.
Yeah.
Does neural networks vector machine can handle the natural data in their raw formats? What do you mean with natural data in their raw formats?
Biological data sets.
Okay, well, usually you will need a pre-processing step, usually, like more 90% of the times, because one thing that pre-processing apports you is that you truly become an expert on the data you are going to use, and also because maybe this data or this data set that you are using is not structured as what the neural network needs. So with that, you can just readjust this data in order to match the necessity of this network.
Ma'am?
Yes, Swapna, you can.
A very nice presentation, ma'am. Ma'am, you are a biologist. Now you are into this computer machine learning, this thing. How difficult was your journey, and what are your suggestions for us to go in the same path now?
I'm sorry, I couldn't hear you right. What was the last part of the question?
I mean, what are your suggestions for us to go in the same path? Because I'm also a biotechnologist, but I want to shift to machine learning. Yeah, so I want suggestions or what could be done if I want to go in this field.
So I recommend you to get into any project you can, if you are interested, of course, but jumping into different projects, for example, as I did, volunteering as an Intel software innovator, or joining the Leukemia Association. This brings you in contact with many professionals in the field. Also, you need to know that in these emergent technologies, multidisciplinarity is really important. So don't be stuck only into, for example, bioinformatics, but also pay attention into which projects might need a bioinformatics person. So with that, you can acquire more experience and also more input from different sectors.
Yes, yes. Thank you, Esther. May I request Krupanidhi sir to give his conclusion remarks? Yes, yes.
Thank you. Thank you for this opportunity.
Yes, yes. Krupanidhi sir, our head of the biotechnology, will give his concluding remarks. Please be wait, Estella. Yes, sir. Go ahead.
Madam Estella, I am heading the Department of Biotechnology, where our Abraham is one of our colleagues here in India. So we are glad to have Dr. Estella with us in this afternoon, that she has given a wonderful presentation of electronic health records and artificial intelligence, wherein she has taken the example of leukemia, also acute and chronic leukemia, wherein the lymphocytes and leukocytes, that is levels, particularly myeloid peroxidase enzyme is involved there. In addition to that, she has also given several image analysis, CT scan, and other analysis. And she's also given us to get ourselves volunteered in the Leukemia Association, so that we can learn more, we can interact more, we can get exposed to the more experts in machine learning and also in artificial intelligence tools. So thanks a lot, madam, for sparing your time. And we all get connected to you through your emails and see that we'll be part of your glorious activities. Thank you, one and all.
Thank you, sir. Thank you, Estella, for your great interactive session. With this kind note, can I end the session? Thank you all. We'll meet tomorrow.